Okay, so let's conclude this long session discussing about Kubernetes. Kubernetes takes advantage, of course, from what we discussed so far. So the cloud computing mostly, there are Kubernetes solutions also for edge computing, and mostly Docker containers, because Kubernetes runs Docker containers using an approach which is called orchestration. Let's start with an analogy. So let's think about carriers containers across the sea, so a cargo ship. Host application are like containers, and these are within a worker node. Okay, and then we put the worker node there on the right. Then the control ships we have to managing and monitoring the cargo ships. Okay, so understanding what happens inside the cargo. So we have to manage, to plan, to schedule, to monitor. So all the logistic stuff that really in concrete in a cargo ship we have to do. And this is done by, let's say, the mind of the situation, which is the master. Let's put the master there on the left. Then at this point, this is, I mean, the architecture that we have. So Kubernetes implements one master and multiple workers. Really, the master could be also more or one. But in a traditional approach, we have one master and multiple workers. Let's focus now on the master components. So one of the goals is identifying the placement of the containers within the cargo ship. So identify the right node to place a container is the analogy that we have in computer science. And this is done with a scheduler that in Kubernetes is called kubescheduler. And we put the scheduler within the master. So the master has already the logic to understanding what is the right node. We will see the node, of course, is one of the worker node. We're installing the container. Then, I mean, which containers are on which ships and when were that loaded, okay? So we need to maintain track of the containers that are sent with the cargo ships all around, I mean, the world, no? And the analogy that we have is which container, I mean, is deployed and in which of the workers and when it was loaded. And this is done in Kubernetes using the etcd cluster. And we put the etcd cluster there in the master. Still, continuing the analogy with the cargo, there are the offices, the operation team office for handling and control of the ship, the cargo team office to verify if the container are damaged, so ensuring that there are new containers if container needs to be rebuilt, and then the IT and communication office, so to have a communication between the various ships. No? And how we do it in Kubernetes, we have a node controllers that takes care of the node, is responsible for the new nodes inside the cluster and the availability of the nodes. Then we have the controller of the replicas, assuring that there is the desired number of containers that are running at the same time. And then the controller manager that manages all these controllers in a place. So the controller manager is another component of the master. How these services communicate with each other, because they are already different microservices, the scheduler, the etcd, and the controller manager, they do it using a API server, which is called Kube API server. So a primary management component of one of the version of Kubernetes, like the K8s, it is responsible then for orchestrating all the operations within the cluster. It exposes APIs. that are used by the users to perform, of course, all the management operation into the cluster. So to control the cluster, to monitor, to understanding what is the status. So we have the API server, and we put the API server there. And as we said, we access the API server by means of APIs. And these APIs are fruitable using a kubectl, so a command line, or a user interface. So, in a nutshell, installing, of course, Kubernetes, then we can understand, the status of the components that we have in Kubernetes using some command like this. There are different, really, installation of Kubernetes that are available. For instance, for the demo we will do in the afternoon, we use really another one, which is much more, lightweight for edge devices. But this is one, the K8S, which is quite common in the community. And with this, we can see that we have, for instance, a master in the node 1, which is ready. It's a CentOS Linux version 7, and it's a Docker container. There is an IP from which we can contact it, and then there are, of course, multiple nodes. And we can see, the status of the components. So the scheduler, the control manager, the etcd, we can see that the status is healthy, and the message is okay, or healthy true. So we can see from here we can monitor the architecture of Kubernetes. We still didn't run any containers inside. So this is about the architecture of Kubernetes. The containers that we run are typically in the workers. So the worker is the part that we have here on the right. As I say, typically there are multiple workers, but let's focus on just one worker. So our worker node is like this. So typically, there is, continuing the analogy, the captain of the ship that manages all the activity of the ship and lets the master node, in our case, shipping, knows that they are interested to join. So the captain is to report back the status of the ship and to report about the status of the container. So of course, the captain is responsible for controlling, checking from a near distance, the containers. This is done in Kubernetes with the kubelet, so an agent which runs on each node of the containers. And then we put the kubelet inside the worker node. So we can see now that we already divided the worker node into different environments, okay? So the Kubernetes is that component that allows the communication with the API server of the master. How does the cargo ship communicates with each other? This is done using a kube proxy that enables the worker nodes to communicate between each other. This is done, for instance, if we need that a backend communicates with the database, or that a front end can communicate with the correlated backend. So the kube proxy will be put there in the worker node. It has access to the public internet, okay? Because then, of course, we have to enter the internet for making some specific performance computation. Now let's talk about pods, because pods are small components that we can see there in the worker node, and these components contains the containers. So in Kubernetes, the containers, for instance, the Docker containers, are put inside the pods. So, of course, Docker is exactly the popular container engine that we already discussed before. So we can see that the overall Kubernetes architecture is the one that we have here. So just to recapping, using this analogy, so we trying to understand how to manage containers, but to manage containers within a complex infrastructure, of course, we needed a master. The master was able to understanding where the container are, to controlling, I mean, the status of the container, and to, of course, allow the communication between the user of the containers and I mean, the administrator of the containers and the worker node. In the worker node, we have really the running of the containers. And again, the containers are put inside the pod. Consider that this worker node is not just one, as I say, there are multiple of them. That's why the scheduler is important, because the scheduler understands if a container is in the worker node 1, 2, or 3, and inside the worker node in which pod the container will be located. So I mean, we have here just a understanding of the pod. These are the concepts that we will see. So from the bottom, we have the virtualization, so the concept of virtualization. Then we have in Docker the concept of the container. And in Kubernetes, we have the concept of the pod. So why it's really important that we use Kubernetes now before to go ahead? Because I mean, could be just an overhead of management, the complexity of the infrastructure. But as you can understand, I mean, she's splitting a monolith in a microservice architecture. From one side, it increases the management of the architecture itself. But on the other side, if the microservices becomes really a lot, it becomes really complex to manage them. It cannot be really just managed by one single machine, one single node of our cloud, but we need multiple nodes where these microservices need to be deployed. And still, considering that we have the concept of horizontal scaling, so the replication of containers, even if we have already a lot of containers, different containers, could be that some of the containers is replicated, because some of the containers has an overload of requests, which is not manageable by just one container with specific resources. So we need to scale it. We need to replicate it horizontally. So Kubernetes enters in the game. It's an idea of Google at the beginning. Enters in the game to help in the management of this complex scenario. This complex, I mean, microservice architectures, and specifically where we have really a lot of containers deployed. It helps to manage, I mean, a cluster of nodes, and it helps at that point to orchestrate them. What does it mean, orchestrate? Means that we need anyway a brain that understands a service is running out of resources, for instance. So it needs a component that monitors that the service is using so much memory. So generating an event. And with this event, the service could be scaled. Could be scaled again vertically, increasing the memory, or could be scaled horizontally, replicating the service itself. This brain is Kubernetes. And after that, we have Kubernetes, then we can easily manage such amount of containers. So how pods are deployed? So this is the main question, because our application, the one that, I mean, the developer builds, let's imagine about, I mean, just a model, no, an artificial intelligence model, or also a web service with a front end, a back end, and a database. This is built, of course, in a container. The container is put in the pod, but how are the pods deployed? So that's the point. So typically, we have in input one or more configuration files. We will seal them. They are written in YAML as well. We inject this configuration file to the master. The master reads the configuration file. Something in the configuration file could be fixed. So that means one pod where there is the container needs to be deployed in the worker node 1, and we don't want that this is deployed elsewhere, or could be such elastic. And then, is the master that, understanding the resources available all over the cluster, decides what is the best place where deploying the containers. So the containers, as I said, could be scaled, accommodating the increase in traffic. So one single container, as we see here, could be replicated. So that means replicating also the pod where the container is located. Or what if the resources are not sufficient? Then we create a new worker. Okay, now we have the worker 2, and then we moves or we add new containers within the worker 2. So in this way, our workers could load balanced for having a decreased, of course, overload of computation and communication. Consider that the worker is typically one node, one machine, and so that means adding new machines into the cluster. So we add the new node into the cluster. The other thing that we can do is also putting two containers in the same pod. Okay, and that could help in scaling the service itself. About Kubernetes and Docker, still Kubernetes helps to manage the networking. So it's like mapping the features that Docker has, okay, like the networking, the volume, and so on. But we have to map them into pods. So the two pods have two different, of course, network interface. So they are part of the same subnet. There is a main controller, for instance, in the pod 1 over one port, the 8080, a supporting controller over another port, like the 3000. Then using, the IP associated with the pod, then of course we can communicate with the other pod, which is in the same subnet, which has another supporting controller. How these containers, inside the pods instead can communicate with external node? This is, another important question, because they do it, using, the IP address associated with the pod and the port that is associated with the service inside. So over the 10.0.30.50, over the port 8080, it's possible to access, first of all, this pod, and then specifically the main controller. Same story, is valid for the supporting controller, and of course also the supporting controller on the pod 2. So it uses, the common networking approaches. So the utilization of the network layer for the using of the protocol IP, and the transport layer for the utilization of the sockets, and then opening ports for allowing the access to this specific service. But at the end of the day, how one pod instead can talk with another pod. So the idea is to have this inter-pod communication. Well, typically this is done by implementing the pod network. So as we did with Docker, where in Docker we created our network, okay, and this network was then used to put inside the front end, the back end, and the database. To make an example, that means these three containers are visible just in that network. Even Kubernetes, of course, has to abstract this facility, and it creates the pod network. So over the pod network, these two pods can communicate and can see, can be visible to each other. How this take place? We have the localhost that allows the two containers within the pod to communicate with each other. So we have like a localhost 8080 to arrive to the main container, but from the supporting container, and vice versa. So from the supporting container, we use the localhost 3000 to be reached by the main container, and then again we have an external, I mean, interface with this pod IP is a subnet created in the pod network to communicate with the external world. As I said some slide ago, there is one or more configuration files that are put in input to the Kubernetes master. These configuration files are called manifest. They are typically the pod manifest, and they are used to specify what the pod does. So this is a nginx pod. So we are in the similar example we made for the Docker introduction. We label it with the name, okay, nginx pod, and then we specify some other details. So we have containers. The name of the container is nginx. The image from which the container is created is nginx latest. This will use the same approach of just only Docker. So that means we have the Docker registry, which will be queried in order to download the nginx container, and then the ports. So we have to specify what is the container port that we have to map, and this is done, for instance, for the nginx, of course, the port 80. This is the port of the guest, okay? So the port of the container, the service inside the container. Then for creating the pod, we do it as it is written here. So kubectl, so create, and then we specify the template of this specific pod, so this file, and then we see, I mean, a message that the nginx pod, which is the name of this pod, is created. And then with kubectl get pods, we can see the status of the pods running in the machine. And then we can see that there is the nginx pod, which has one replica, is the second element of this number. And then one replica is available. So 1/1 is currently available. The status is running, didn't have any restart, and the age is 22 seconds alive. So this is, I mean, the way in which we can create, of course, the containers. So we get the pod like this, and then we verify the operating system, for instance, with this with this command line. So this is over a Debian, and we can see like this that we have much more information from the pod. So the pod is running, but we see also the IP now. So 10.44.0.1. The node is the node 2, and then other information that currently we are not filled up. But then we want to use the service which is inside. So for instance, inside our nginx server, there is a web server that is just showing a demo message. So we curl. So we use a command that in Linux, but is available also in Windows and Mac, but typically Windows needs to be installed. So curl is a HTTP request client. So curl like this makes a get. So with the get, we get the object from the web service, and we have under the 80 port of this IP address, the object which is behind, which is the web page, of course, not formatted in HTML, with just a text hello shell demo. Of course, this could be run also in a browser. It will be showed up in a browser, but if there is an HTML, it will be rendered in as the CSS, specifies. Let's see now what is the life cycle of a pod. So the life cycle is that we start from having this manifest. We have the API server, of course, in the master. Then the pod could be pending. Okay, from pending, the pod could become failed. So there is some error, of course, in the pod, and this means the pod is not running. Then the pod could become running, and then the pod could become succeeding if the operation inside the pod are all completed and the pod doesn't need to do nothing else. How can we ensure at the end that free pods replicas are always available and running at the same time? We do it with the concept of replica set. So as I said, I mean, it's important in terms of cloud computing and the management of microservices to maintain a set of replica or to specify what could be the minimum amount of replicas that microservice should have, or also the maximum amount of replica that service should have. I mean, just options, settings, parameters that we can add to these devices. So we have to ensure that the number of pods are running at any time. So Kubernetes needs to know what is the idea of the administrator, of the creator of that manifest in terms to be adapted to the request. So the point is that if I ask for having always free pods of the same application, if one pod fails, the system needs to be able to rerun it. Okay, in runtime, and this is done, of course, with the replica set. The replica set have pods and typically associated with labels. Replica set is the next generation of the replication controller that Kubernetes has. Both serves, the same purpose. So the replica set is a set-based selector, while the replication controller uses a quality-based selector. About this, the label and the selector, when the pods are scaled, the question is, how are these pods managed at such large scale? Because we need to understand. So mostly the orchestrator needs to understand what our preferences in terms of deploying of these pods, and so understanding what is the worker where these pods needs to be deployed. So this is, the specific of a pods with labels like app, guestbook, tire front end, environment development. So these are, labels that we can add to the pod that will help us to match this label with the label of the workers. And we are specifying the number of replicas, for instance, like 5. So we would like to have 5 replicas of this pod. In the equality-based selectors, the operator is equal and double equal, or in the set-based selector, in, not in, exist. So an example is environment production like this, or environment in production QA. It's another, is the translation, let's say. So the command line in the first case is this one, because kubectl get pods -cell environments needs to be production, while here this environment in production. In the manifest, we have the manifest for the quality based, which is the one I showed before. For the set based selector, it's something a bit different. We have to match expression. So the key is environment, operator in, and the values is of production or QA, for instance. And the tire is not in front end or back end. Okay, so in this way we can specify, we can try to custom the deployment of our architectures, our microservice in the architecture. Okay, so this approach is supported on all the resources, such as replicas, controller, and service. Why this other approach, the one on the right, is supported for replica sets, deployment, job, daemon set. This is just a matter of different also version of Kubernetes, different features that were implemented in Kubernetes during the time. About, I mean, the replica set, of course, it's important to understanding what is the manifest file. Manifest file, having some understanding, I mean, how does it test when the node fails, scale up, scale down, and so on. Yeah. So the replica set manifest file could be something like this. So we have the kind is of this configuration file is a replica set. So this is the type. The specification is having two replicas. The selector match the labels is an application and Nginx application. We have some template, okay, where we have metadata. We get the Nginx pod and we have the label app Nginx application in the entire front end. And then we have specifications about, I mean, what is the container. So as we did before, Nginx over the port 80. So we create the pod like this. We have the YAML file. We have then the pod, I mean, created in our cluster. We can see with the kubectl get pod, I mean, -l, we specify the label. So that means we can see only the pods that were labeled front end, and we can see that they are two. Why they are two? Because there are two replicas. Okay, so that means we have two replicas of the same pod. We can see, I mean, here the get rs, I mean the replica set. We can read.
خليني اتكلم بقول لك شيء بس ما جيتش تون.
Okay, there is some noise in the background, so maybe you can switch off the mic. In the meantime, I go ahead. We can see here that the desired number of replicas is 2. The current number of replicas is 2, so it's working quite well since 12 minutes, for instance, in this example. And of course, we will have more information with the wide option. So containers and Nginx, and the images is Nginx, and the selector is this. Okay, so again, this is to understanding, first of all, what are how to manage the replicas, and how to decide, I mean, what will be the workers, the nodes where we have to deploy them. So we label the pods with specific, I mean, attributes, arguments. With this command, we have much more information. We describe the replica set. Again, two currents to decided. The pod status is that two are runnings. The pod templates, we could see the labels. So application and Nginx app, tire front end. So one is more dedicated to the application, we can see. So it's an attribute that only the Nginx application will have. The other one is a tire that will be, I mean, much larger in terms of application, which is front end, because we could have an Nginx, but we could have also another front end for a mobile device, for instance. So we will put this label also to the other containers. About the containers, we have some information. We can see it's really one-to-one with the YAML file. So we have image Nginx over the port 80 in TCP. Okay, there are no environments variables, there are no point of mounts, there are no volumes, so these are not, of course, described, or I mean, described with a none. And then there is a list of events. The events is a normal event successfully created from the replica set controller, and this is, I mean, the message, and this is the name of the replica set. Okay, we can decide then to scaling the Nginx service later, because we understand that the replica set are not enough. So that means we want to extend them. So now the replicas must be 5, for instance, no more 2. Okay, so this is a matter of the elasticity of the cloud computing, and then we can do it, I mean, just using this command. So kubectl scale the replica set of the Nginx replica set using the number of replicas here plus some option more. Okay, about, I mean, the deployment, we have deployment controller provides the updates for the pods and the replica set. Typically, we describe a desired state in a deployment, and the deployment controller changes the state and to the actual state to the desired one. Okay, and it's possible also to create to define deployments for creating replica sets. Or again to remove deployments, or again to have new resources within the deployments. So a single deployment manifest file will have, the characteristics to understanding what are the number of replicas and what are, the pods. So do we need to create 3 different manifests for each of these, for instance? Of course, the answer is not. We can create all 3 different objects using one single deployment manifest file. Okay. The features that the deployment introduces are the multiple replicas, the upgrade, the rollback, scale up and down, pause, and resume. So let's think about the recreate, okay, like it's one of the deployment times. How does it work? Shutting down the version A and then making sure that the version A is turned off, it brings up the version B. Of course, there are disadvantages because during this deployment, there will be some downtime of the service. So, but at the same time, it's easy to set up. Then we have the rolling update, ramped or incremental. This is the defaulting updating strategy in Kubernetes. It could take some time. How does it work? This roll out a version of an application by replacing the instances of the one, that was successfully rolled out. So let's assume that there are 10 instances, for instance, of the version A, which runs, behind a specific worker. So then we update the strategy that starts when the instance of the version B is deployed, and when the version B is ready to accept the traffic, then the version A is removed from the pool. So you can understand here that the disadvantage that we had before is not present. So we have anyway the service always running. So we start the rolling out. We anyway put the service B already running. When the service B starts to accept traffic, then we remove the version A. Then we have the canary. Is an ideal deployment method for someone who wants to test a newer version before they are deployed, entirely deployed. How does it work? It gradually shifts the production traffic from version A to version B. So that means if we have 10 instances of the application A running inside a cluster, using this deployment, we can maintain, the reception of the requests both on the A and the B. In this way, we can start, using the B and understanding how does it work. And then when all the updates, so the 10 instances moves from the version A to the version B, when this update is completed, then all the A application can be removed. Another deployment time instead is the blue-green. Is an instance for rolling out or rolling back. Using this method, we have a version B, which is labeled like green, which is deployed along with the version A, which is deployed like labeled like blue, with the same amount of instances. After testing, new version with all the requirements, the traffic will be switched from the version A to the version B directly. So from the blue to the green label. We will see now, short demo here, just some slide about the deployment. This is a deployment manifest where we have the kind, so deployment. We have a specific part for the replica set. So we have 3 replicas. We need to match the labels, so Nginx application, even in this case. And then we specify the pod. And in the pod, we have the container, which still maintaining the same example, is the Nginx. So we can see here that we started with the one manifest of the pod. Then we extended the manifest of the pod with the replica set. And then, as we said before, we don't need three different or two different configuration files for making a deployment, but one manifest file, so one YAM file that includes also the replica set and the pods. So we can see here how to create, this deployment. So there will be three replicas, okay? At the beginning, when we deploy the YAM file, we expect to have three replicas. They are running, okay, so they are now pending to be to pass in run. So after just 6 seconds, and then after a while, we can see that more or less 1 minute, these three replicas of Nginx are ready, and the three of them are available to be used. So at the end, the deployment is a way to have the pods and the replica set. So we can get here, information from the pod, the replica set, and the deployment, like this. Okay, then we can see these are the pod. This is the replica set. So desired free, current free, ready free. And then, the deployment extension, we have information about the configuration that we injected into the system. Then, in this way, we have three instances of the same Nginx application that are running in the same pod, okay? In the form, running in the form of pods. Sorry. These are deployed, in different nodes. We can see they have three different, indeed, IP addresses. So one in each pod. And then, we again see in this way only the deployment that are labeled with the Nginx application. So in this way, we can just filter the deployment where we have the Nginx application. Still, we have here the same for the replica set, and then, we can set some image deployment, okay, updating it. And then we can see the creation timestamp for this, the annotation that we have, so deployment Kubernetes, the number of replicas desiderated and updated, the rolling updated strategy. So when there is the 25% of the max unavailable services, then it operates, rolling it up. And then, the pod template with information about the container. Okay, again, this is a zoom of the other one. And then, for scaling it up, the deployment, we can see that deployment Nginx deploy, we specify now the number of replicas, which is 6. We can see that from the kubectl get deploy, we have a different number of replicas available now. 6 are the replicas required, but at the time only 5 are available. So 5 over 6 are available, and we can see here all the pod with 6. After a while, then we had 6 replicas available, and we can see them here. So 101 ready, and so on. We can list, of course, the pods by labels. This is with the label Nginx applications. These are all the pods with the same label. And then, we switch now to the concept of services, and then we are going to complete the discussion about Kubernetes. So services, they are there because, for instance, we have been asked to deploy a web application. And the question are, how this front-end web application is exposed outside the world? How do front-end app connected to the backend? And how do resolve pod IP changes, okay, when they die? Because when the pod die and then is again up, of course, the pod could change the IP address. or if the pod is migrated from the worker 1 to the worker 2, of course, it could change also the IP address. Well, let's think about it. We have a front-end service, so a service which stays between the user, which is here, and the front-end pod, which is here. And then we have the backend service, which is a service which communicates between the front-end pod and the backend. So we have different type of services. This one, I mean, the cluster IP, node 1, I mean, is reachable within the cluster, connects the front-end pods to the backend pods. Then we could expose the front-end app to the external world, and then we could have services for instance, load balancing, for regularly distributing the loads between the available workers. Cluster IP, I mean, let's imagine we need to deploy one full-fledged of application, for instance, front-end, back-end. The question is, how can we restrict the access of backend to only the pods that are within the cluster? Because typically, of course, I mean, the users cannot access directly the backend, but they access, of course, the front end. And then we do it like this. So we have the user access the infrastructure, I mean, with this IP and port. Then we have the service will communicate with the front end. The front end will use another service, and with this service redirects the requests, not balancing them, to the backend pod. Okay, and so that's it about, I mean, the Kubernetes. So I guess we have time for some question now. That's it.
Hello. Sorry. Hello. At some point, you used at the beginning, you used the terminology worker,
Yeah.
and then you were talking about cluster and pods.
Yes.
I got a little bit confused about that.
Okay. Well, the architecture of Kubernetes is a master worker architecture. So that means Kubernetes runs at least one master and multiple workers. These workers are at the end node, and this node could be distributed over distributed systems. These workers could be part, of course, not just of one single machine, but one worker could be deployed. Let me make an example here in Messina, another work in another institute, but they are still part of the same cluster. Okay, so this is a cluster, the Kubernetes cluster, where the master can still reach and schedule pods inside these workers. It's possible to have also multiple masters. That means that we can move the brain of the master worker architecture. Not only, let me again doing the example here in Messina where I am, but also in the other institution. So that means the other institution is also able to understanding how to schedule the pods and to allowing, I mean, the administrator to injecting new deployments, new YAML manifest, for instance.
And pods, they reside physically on worker nodes.
Pods, they are physically inside workers. It's really a wrapper of one or more containers. Is let me say, another abstraction that Kubernetes introduces for managing containers, but is an important abstraction because with the pod we can group one or more containers and we can decide to set up a specific number of replica for that pod. We can decide to set up a specific number of, kind of deployment for that pod. So it's, a wrapper of containers, but if you saw, all the, potentiality of labeling pods, labeling replicas, labeling deployment, in this way is possible when of course, the architecture of microservice grows up and becomes difficult to manage, I mean, is a tool for creating a better management of all the containers. So we have a cluster. Inside the cluster, we have a master and multiple workers. Inside the worker, we have pods. Inside the pods, we have containers.
Okay, thank you. And the other question I had was that it looks as Kubernetes could become quite complicated to configure and run. So I was I've used something called Run AI, which I think sits on top of Kubernetes. But I was wondering whether there's frameworks which abstract all the complexity of Kubernetes, which could also be free for poorer entities like universities.
Well, that's true. Kubernetes is not easy at all. Anyway, it's really a tool that you need to study a lot, and things could become really complex when the microservice architecture that we have underlying is really big. We can see that we already have a not so easy readable manifest file for just one container, because at the end we have only the engines. What I can say that, I mean, me personally, I'm also doing research in this direction. I mean, in having some artificial intelligence behind Kubernetes, in order to facilitate, I mean, the creation also of these manifest files. Okay, because of course the creation of the manifest file is currently a bottleneck, no, because it's not so easy. But if there is a recommendation by an artificial intelligence, okay, it could be really a good help for the Kubernetes administrators. So I'm currently doing research also in this direction.
Okay, great. Thank you. Thank you very much.
Thank you.
If I I'm trying to understand, like, this is the first time I ever actually look into Kubernetes, so I was trying to understand what the general concept is. So this is like, it's a framework that essentially lets you implement like a whole microservices architecture and has a central point to manage all of it. So you have like a bunch of Docker containers, for example, that all have separate microservices, and you can have mass operations on all of these and as much as you may need.
Yes, you are right, but not only this. Think about what we discussed before with Docker. We started from the Docker file. The Docker file was able to run locally one single container. Then we moved to the Docker Compose. Docker Compose was able to run locally multiple containers. But with Kubernetes, we can run multiple containers also in a distributed fashion. So I don't know where the worker is, but there is behind the network. And with this network, I mean, the master knows where the worker is and can distribute the architecture all around the web.
So yeah,
So
so it's like, it's also like distributed architectures as well. Distributed.
It is. It has also, I mean, I didn't discuss about it, but there are also logic of offloading. So understanding, I mean, if one worker is out of resources, for instance, memory, because there are too many containers inside, then we migrate one container from one worker node to the other worker node. Okay. So at the end of the day, we can have also concept of federations inside. Because if one worker node is managed by my organization, another worker node from your organization, this is a federation, okay? Because we have two different regulations, we have in two different countries, just to make an example, but still it's part of the same cluster, okay? So it's an evolution of the system. So one single container locally, multiple containers locally, and then multiple containers.
Okay, I understood. Thank you.
You're welcome.
Hi, here from my side, I have some question regarding the GPU usages with the Kubernetes cluster. I have used the Kubernetes cluster for some time, and I realized that it does not good at sharing the GPU resources between pods if I'm using the native Kubernetes. I'm not sure if there are any good plugins or is there any methods so that we can fully utilize the GPU resources with the Kubernetes cluster. Do you have any suggestion on that?
I mean, I never did really, but I'm quite sure there will be some plugin that helps to install some CUDA, for instance, dependency, and to virtualize GPU. The point of virtualizing GPU, because it's some issue that we had in data center that we have here in Messina, is that, I mean, it's not so easy. I mean, you need to buy also licenses. Otherwise, I mean, you can just add the entire GPU to a virtual machine, but it's not what the virtualization does. Because the virtualization takes, I mean, my computers, let's say, and split it in parts. So takes my 8 cores and assigns 2 cores to a virtual machine, 2 cores to another one, 2 cores to another one. I have 16 gigabytes of RAM. Well, 2 gigabytes to this virtual machine, 3 to the other one. So with the GPU, I mean, the main issue is that if you don't pay for the license, the virtualization license, that typically is provided, I mean, asked by the manufacturer, so from NVIDIA, but the NVIDIA GPU, you can just attach the entire GPU to the virtual machine, but it's not virtualization, you know, it's just one full resource attached to a virtual machine, is one-to-one. So there is this just things to be managed, and then it's matter of virtualization, mostly then matter of orchestration, let's say. Then for the orchestration, I mean, I never did, but I'm sure there will be some tool to monitor the use of the GPU, making some replica, some scaling policy according to the usage of the GPU, and then using the GPU in containers. I mean, Google does it at the end of the day. I mean, we just rent a GPU and we use a virtual machine because the Colab notebook is inside the virtual machine. And they attach, I mean, part of a GPU to that Colab notebook.
Lorenzo, just give a question. There are other ways to do distributed computing. For example, you can use ROS. Why should we go to Kubernetes rather than use ROS?
Well, this is a nice, interesting question, because there is a new trend also in cloud, which is cloud robotics. No, cloud and robotics. I mean, they are trying to merge the two community in this sense, in order to make deployments. I mean, to management the fleet of robots. The point is, ROS is an application which is possible to be containerized. So that means if it is a container, we can use all the facilities that we have seen before for the Docker, so Docker build, Docker run. We can create our own ROS package using Docker. But when the fleet of robots that we have is quite big, then, for instance, our enterprise organization manages a fleet of robots in a location, then in another location, then of course we need some tool behind to manage the deployment over the robot infrastructure, and we do it with Kubernetes. The second point is that the robot today could be considered in the distributed system domain an edge device. So that means it's a device that has limited resources, is battery powered. So it's a device that can run some computation, but we are not sure it can finish the computation. So maybe we need to offload the computation from the edge device to the cloud. And so still with Kubernetes, and anyway, cloud computing and edge computing in general, I mean, this could take an advantage. That's the main reason.
Okay, thank you very much, Lorenzo. Now let's move to the next speaker. Is Dr. Palese. Thank you very much for your 3 lectures. Is Mr. Palese here?